Electrostatics 17. The lesson on Gauss law still continues. We have stated Gauss law already. Isn't it so? Isn't it so, Shivani? Can you tell me the statement of it? The mathematical statement of it, quickly. Shivani, are you listening? Shilpa?
Yes.
Tell me the statement. Look into your notes. Now, I was calling you in the very beginning because I wanted you to be attentive in the class, right? Quick. E dot dA is equals Q enclosed by
E2
epsilon 0. This is epsilon. What is that epsilon 0? Electrical permittivity. Permittivity of vacuum. Did we not state this law already? Then when I ask you, why are you not opening your mouths? Now we'll go for applications. Some time ago, we have written down the electric field of shell of charge and sphere of charge without proving it, because at that point of time we thought proving it requires a lot of mathematics if I applied inverse square law or Coulomb's law. What do you say? One of you speak, don't sit like that. We have stated the thing: inside a shell it is 0, outside it is equivalent of point charge. Like that we are making statements.
Yes.
But if you remember, in gravitation, we applied Gauss law for gravitation and got the values of gravitational field strength. So in a similar way, we'll be doing it now. First of all, a shell of charge. We simply have a shell of charge like this. Of course, I am drawing that circle in the beginning so that my life becomes easy to put shell of charge. But when I said shell of charge here, first of all, I'm taking spherical shell. Yeah, let me mention that. And later, what I was trying to tell you was it is only the charge which is making up the shell, I'm saying. The sense, I need not have to worry where is it sitting. So radius r. At a distance r greater than r, I would like to find out the electric field strength using Gauss's law. For that, I'll imagine a spherical Gaussian surface. So imagine a spherical Gaussian surface. Now, a spherical one we'll imagine, because from symmetry, E will be all over same. In fact, let us show even the field lines. because the field lines symmetry will tell us what kind of Gaussian surface we should choose. Keep listening to my words carefully. And see, the moment you put a charge there, for every charge, there should be a field line. So I was struggling to adjust those lines because the charges were put very close on the other side. So this kind of a charge lines spread will be there. So at a point here, all over the sphere, E would be same from the symmetry of the lines, because if I look at the density of lines, the number of lines per unit area anywhere here on the spherical surface, that will be same. Therefore, E will be same all over the Gaussian surface. This is imagine a spherical Gaussian surface. There's no surface as such. To find out E, we are just imagining that. Now take one dA element whose direction is along the outward normal, and this is the direction of E. So flux through this elementary area or area dA would be d phi E electric flux is equal to E bar dot dA bar.
Yes.
Which is E dA cos 0. Why? The angle between vector E and vector dA is
0.
You need to all the time understand one thing. dA as a vector is this way, but the actual area is here. Try to understand. Right? So this is simply EDA. Now, what does Gauss law say? Here itself we wrote integral E dot dA is Q enclosed. The total charge is Q. Q enclosed by epsilon 0 here. So we know, and this circle shows closed surface. Okay. EDA cos 0, what we wrote already there, I'm writing here, is Q by epsilon 0. Since E is supposedly constant, integral dA is equal to Q by epsilon 0. This is E into 0 to pi r square, you can say. That will be E into pi r square, 4 pi r square, I'm sorry. Q by epsilon 0, 4 pi r square is the surface area of a sphere. So E comes out to be 1 by 4 pi epsilon 0 Q by r square, which is that of a point charge. Okay. Shreya, you're not there? You're there. Many are not there. So that means for an external point, this is equivalent to having all the charge on the shell at the center, which we've been telling many times by now. But see the way it was done in detailed way once again. To do this from inverse square law, the Coulomb's law will be slightly mathematically long. That's why we kept it pending for Gauss law.
Here, instead of a spherical surface, if we
Hmm.
take another surface, then
Also, the
find the solid,
other surfaces projections will once again make only
the same spherical
same
surface, and
yeah.
we should take the solid angle.
Yeah, we should take. We have already taken. Even if I took something like that, huh? Like for example, I don't want to spoil it, but since you asked, I'll show you. Let me take a laser pointer or highlighter. Laser pointer I'll take. Okay. Now I'll take this kind of a funny surface, for example. Do you understand?
Yes,
So
sir. Like hemisphere.
the projections of those things are only once again the sphere, right? So the
Yes.
solid angle is same. The flux is same. Do you follow?
Yes.
One surface, if I take, this is the cap of it. The projection of that area is this. Like that, whatever surface you take, finally all the projections will be only the sphere once again.
Sphere.
So the solid angle is same, therefore flux is same. Do you follow?
Yes.
Right. So can I continue?
Yes, sir.
Others?
Yes.
Monica, Shilpa,
Yes.
Yes, sir.
Vedanti. Are you there?
Yes.
And what's your friend's name? The other girl? Omeshwari. Are you there? Sneha? Srikantha? Aditya Reddy, are you there?
Yes, sir.
And what is the other fellow? Tejas? Okay. Now, it implies for all the external points, tell me.
The sphere is like a point mass.
The shell of charge. Shell of charge behaves like what?
Point.
A point charge at the center. Point charge at the center. Okay.
Yes.
Yes.
Now, all this is charge again. Now, just at this point on the surface, you will take a Gaussian surface very close to it, okay? So simply I can put the previous one at r equals r. All these lines are there, children. The lines of E. Hello. So
Yes.
at r equals r, I'll get E equals what? E equals 1 by 4 pi epsilon 0 Q by
R.
R square.
Capital R square.
Now at R less than R, somewhere here, imagine a Gaussian surface once again. This is a Gaussian surface. Huh? If E were there, it would be once again symmetrical only. If it was there, for example, inside. Huh? Hello. So therefore, I can write E into 4 pi R square. What is E into 4 pi R square? E dot D, all that integral. Huh? Is equal to charge enclosed is what? 0. So E equals 0. Why did I say E would have been same? Because E dot dA can be 0. Huh? In two ways. One, E may be 0 or E dot dA may be 0. Neither E need to be 0. dA anyway is not 0. They can be perpendicular, right? Even then, E dot dA will be 0. So charge enclosed is 0 doesn't automatically mean that E is 0. Here I'm saying E is 0 because E is going to be same everywhere. Hello. My point was, if E was different at different places, E dot dA would have been 0 also. If E were perpendicular to dA, E won't be perpendicular anyway, but E is same all over. Symmetry is there, so I could guess that E dot dA is 0 because E is 0. So that's why I said charge enclosed is 0, E is 0. Okay. So E will be 0 inside. So if I take it in a graphical way, E versus R, it would be 0 until you come to R, and from there it changes inversely with the square of the distance. So this is about E for a shell.
Sir,
Hmm.
for R greater than R, if the area is perpendicular, then also it will be 0.
But even there symmetry is there, no? Huh?
Yes.
E is all the time parallel to dA. Okay.
But
So this is the advantage of using Gauss law.
won't it, can it ever be perpendicular?
It will be, we'll show it somewhere. Huh?
Yes.
While doing applications. Okay. In this case, it cannot be because the lines of force are all going radially out. Isn't it so? So E and dA cannot be perpendicular.
Yes.
Okay. Can I continue further? So for a shell, our job is over.
Yes.
Then
Okay. I'll continue, children. Shall I?
Yes.
Yes.
But remember, even for another shape, another shell of any shape, E would be 0. Any shell you take, E will be 0. Can we say from Gauss law, can we justify this from Gauss law?
Charge inside will be 0. So
Charge enclosed is 0. Therefore, E is 0. Okay, I'll come back to that. Just remember this. Huh? Okay.
yes.
Right. Next. Now, all right, we'll come back to the shell business again. Now, sphere of charge. Sphere of charge. Okay. Now, Sriya, can you just tell me how we should go about? The circle is not come properly.
Yes, sir. For
You tell me, I'll do it for you.
For a sphere, we know electric field lines will be from the center.
Just a minute. Let me put all positive charges, uniform charge distribution. That's an important thing. Now, anytime, children, remember, whenever you would like to apply Gauss law, the first thing you should try is, take the lines, field lines. It will be like this only, children. How
Yes.
can you guess? You just superimpose the field lines of many shells. This can be taken as many shells. Do you follow?
Yes, sir.
Right. Now, once again, it goes without saying that I should take what kind of a Gaussian surface?
Spherical.
Spherical Gaussian surface only. Okay.
Yes.
So you'll take one dA as usual, which is this way, parallel to E. Right. Now the total charge, if it is Q, all this charge is enclosed by the Gaussian surface. This blue one is what?
Spherical Gaussian.
Gaussian surface. So, what do we write? E dot dA is Q enclosed by epsilon 0 EDA cos 0. This thing is not changing at all, the derivation, right?
Yes.
For outside. Q enclosed is basically the total Q. So E into 4 pi r square equals Q by epsilon 0. E equals 1 by 4 pi epsilon 0 Q by r square. Very reasonably so, because this can be taken as many shells. Each shell is represented by a point charge in the center, isn't it so? Hello?
Yes.
Yes.
So if you imagine many shells of Q1, Q2, Q3, Q4 charges, Q1 is at the center, Q2 is at the center, Q3 is the center, Q4 is at the center. Like total charge is at the center for all external points. And in a similar way, at R equals R, I could write what? E equals 1 by 4 pi epsilon 0 Q by
capital
R square. Sorry, Q by R square. Now at a point inside, take a Gaussian surface again. Hello?
Yes, sir.
Here. This R less than R. Now the charge includes not the total charge, only this charge, right? I'll call it Q. Hello?
Yes,
So,
sir, it will be less.
Integral E dot dA is equal to Q by epsilon 0 now. Isn't it so?
Yes.
So what do I get? E dA
Cos
cos
0
0 is equal to Q by epsilon 0. That is E into 4 pi R square equals Q by epsilon 0. Q I won't be knowing. So I'll write it as rho into 4 by 3 pi
R
epsilon 0. So what do I get for E?
rho pi R pi 3 epsilon.
So when you plot the graph of E versus R, you'll get like that. This is 1 by R square. This is directly as rho R by 3 epsilon 0. And if you want, you can also write rho for the in terms of the total charge and total radius. That will be E equals rho is what? 4 by, sorry, Q by 4 by 3 pi R cubed. Isn't it? Into R by 3 epsilon 0. 3 cancelling, I'll get 1 by 4 pi epsilon 0 Q. Tell me. QR by
H.
Isn't it so? That's it. So this is about the E of a sphere of charge. Tell me. Okay, can I continue?
Yes, sir.
So all these things I mentioned already, if you remember, but I'm going once again, over and over again and again, so that even if you did not study, it will stick somewhat. Now, so we added, but we are ready for many things of applying Gauss law. Okay. All right, I'll continue from where we left. The summary, many times I've told you, we added these two, but remember, this is not enough. Here, rho is constant. Rho can be varying. So once rho is varying, the integration will be slightly different. All those things I'll give back later, but remember everything. What is done, you can redo all the derivation also. Now we'll continue from where we left. Some problems we'll see. That cube thing, let me take. No, there are still more things. Let me see, finish off those things. After that, I'll come back. The applications are not over yet. Look, E due to an infinite line charge. E due to an infinite line charge. Okay. You know already that. Do you remember the formulas for this? Hello. Do you?
Yes.
Now infinite line charge I'm taking. For this, if you remember, what did we do? Can you tell me? For a finite line charge and the perpendicular bisector, all that we did something.
Yes, we considered the angles and
angles and all that. What do we write the formula? Lambda by?
Sir, E here we got 2k lambda by y. Sir.
Yeah, 2k lambda by y we got for this. K is 1 by 4 pi epsilon 0. Right. So this 2 going away, I'll get lambda by. This was E, we already knew, right?
Yes.
Now, applying Gauss law. What kind of a Gaussian surface I can take? Can you tell me? For that, you need to know the field lines pattern. Remember, I am showing it in 2 dimensions. They are not in 2 dimensions. They are in 3 dimensions. So can you tell me what kind of a symmetry I have? Cylindrical symmetry. They are spread into a cylinder. Do you follow? And at equal distances, the values are equal. One more line like this. I don't want to draw and spoil it. One line into this like this. Do you know?
Yes.
All like this. Hello?
Yes.
So remove that. So what kind of a Gaussian surface will serve my purpose? A cylindrical Gaussian surface. Do you follow? Hello?
Yes.
A cylindrical Gaussian surface I should take. Right? Hello?
Yes, sir.
Why like that? The whole idea is I should be able to take out that E in the integration. Hello? That can happen only if the E value is same over the total Gaussian surface. So what kind of at a distance R, our point should be in that cylinder. So a cylindrical Gaussian surface is taken. Do you follow? A cylindrical Gaussian surface. Now look at this, Shriya. Here, if I take one dA element, this E and D are in the same direction. Hello?
Yes, sir. They're parallel.
But if I take a dA, of course, you may think it is closer here, closer surface, right? We need to take close surfaces for Gauss law. So here dA will be like this and E will be like this.
So then it will be perpendicular.
No flux. Naturally, if the lines are parallel to the surface, no flux anytime. I told you already, if a surface is there, only if
pass through.
It should pierce.
Pierce through that surface, only you got flux. If it is piercing perpendicularly, maximum flux. If it is piercing slantingly, lesser flux. Okay. So for the circular caps, I mean, for the circular caps on the sides,
it will be 0.
On the sides, flux is 0. Do you follow?
Yes.
Hello, children. Therefore, now infinite line charges is. So I can put a charge Q here, total charge in the line charge, but that's not the total charge. Only what is enclosed here I'm showing. Total charge is something else. Let me say this length of the cylinder is L. Okay. Hello. So
yes,
Gauss law application. E dot dA equals this Q, which is anyway not known how much charge is there, but we don't know because it's an infinite line. Only here I thought it is Q. It's not the total Q of the line charge. Q by epsilon 0. So this is written as EdA cos 0 Q by epsilon 0. Shall I write straight away now? E into dA Q by epsilon 0. What is dA for this cylinder? This radius is R, length is L.
Pi RL.
2 pi RL.
Yes.
Cut that. 2 pi R with the length. Sorry. 2 pi R is one side length, L is the other side. This is L. It will form a rectangle like this, right?
Yes.
So no confusion. So what should I write? E into 2 pi RL equals Q by epsilon 0. So E equals, what do I get? Q by 2 pi RL epsilon 0. But Q by L is luckily lambda. So lambda will be known to us. So lambda by 2 pi R epsilon 0. Look at this, same thing we had.
Yes, sir.
But had it been a finite line charge, I couldn't have applied Gauss law. Think over it. Had it been, what did I say? Had it been a finite line charge, there'll be field lines this side also. So I won't be able to know the flux through these caps.
Yes, sir. There'll be an angle that time, and we cannot take that.
We can, but only thing is we don't know the value of E. So the whole idea is finding out E. We cannot take the E out of the integral sign. Gauss law will be applicable there. Don't worry. But using that, I cannot calculate E. E dot dA, that also we should be able to write. But how much is that E? We don't know. Isn't it? But all this E was same. We are guessing because of the symmetry. Hello.
Yes, sir.
So complete it. So when you finish it, tell me, we'll continue. See, we could only show the two-dimensional picture, whereas you actually need to think it is in a cylinder. The many arrows are piercing through that cylinder. You should think. Then you will understand things in a proper way. Okay.
Done.
Yeah. Then one more at least we'll finish. E due to an infinite sheet of charge. This is charge in two dimensions, right? Infinite sheet of charge. See, line charge, shell of charge, sphere of charge, sheet of charge. That means we are thinking of all possible charge configurations, which are practically having industrial applications, children. Believe me. How would I show this infinite sheet of charge, children? I'll show like this. I'll put some kind of a thing like this to tell you that it is extending up to infinity. It's not finite. And let me put charges. Once again, uniform charge distribution. This is sigma, charge density sigma. In the very beginning, I told you how to take this sigma, lambda, rho. Rho is volume charge, lambda is line charge, sigma is surface charge. Now, what kind of a line pattern you get, Lines will be there this side, that side, not to the edges, because edges, it's going up to infinity. Do you follow? So all the field lines in the plane of the sheet will cancel out. You're left with only the field lines which are like this. Hope people understood it. This kind of a field pattern will be obtained. Hello? Tell me.
Sir, in the plane it will get cancelled, meaning because of the adjacent charges.
Naturally.
Yes.
Hope you understood why I rubbed off and put like this. Do you follow?
Yes.
Hope everybody understood this. Now, this will motivate us to take what kind of a Gaussian surface?
Cylindrical.
Like this. Do you understand what did I show here? That small cylinder pillbox is piercing through the surface. Hello?
Yes, sir. Like it's going through the
on the other side.
Yes, sir.
Now look at this. What will I write now? For this, flux will be what, if this area is A, this area. If this is E, this is EA. For this also, it is EA. Right? Hello.
Yes.
And for this one,
it
E
will
is
be
like
zero.
this, 0, no flux through this.
Yes.
So the flux, if I add EA plus EA, both are positive flux only. E and A are in the same direction on both the sides. Okay?
Yes.
So EA plus EA is whatever charge enclosed, this charge, Q by epsilon 0. So 2EA is equal to Q by epsilon 0. So E equals Q by 2A epsilon 0. Q by A is sigma. Just go back and see. We did something like this already. So what it says is, what the model of the situation is this. If there is a single layer of charge like this, infinite one, on both the sides there will be field, and that field will be independent of the distance from it if it is infinite line charge, and it is on both this side, that side is sigma by 2 epsilon 0. Okay.
Yes.
Hello, just try to understand this in a proper way. Hello, children. This is very clearly shown. I want you to really understand it. This my palm, you can see. This is line of charge. On this thing, I've got charge, but this side I cannot see. 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 It is infinite. Do you follow? Then the field lines are going out this way, going out this way. Field lines won't be there parallel to the thing because the adjacent charges will cancel out. So what did I do? I just took one Gaussian surface like this. Can you see this? Can you see my hand? Hello?
Yes.
I think you can see the whole picture also. So this is my what? Gaussian surface. So there is no flux through this because lines are going parallel, or E dot dA is 0. EA this side is equal to charge enclosed here. This much only on my palm, that by epsilon 0. But finally that Q by A will become sigma for the whole thing. Do you follow?
Yes.
This hand you see and tell me whether you understood it. Hello?
Yes, sir, followed.
Now, if I had two plus charges like this, plus sheets like this, I'll get sigma by 2 epsilon 0 because of this in this direction away, because of the sigma by 2 epsilon 0 this way. Superposition tells you that E will be 0 in the middle. Can you see my both the hands?
Yes. I'll get cancelled.
Like it is this way. I'll show an immediate application for this. Look at this. Already fellows are going out. Silly kind of people you have. Look, we have charge like this, This is plus charge. By the side of it, I've got another plus charge. Do you understand what did I try?
Yes, like two sheets will be parallel.
Side by side parallel things. This one, and then another one by the side of it. Do you follow?
Yeah.
Like this. Hello. So this is plus charge, this is plus charge. If you think in the middle of the charges, if I show in this plane, it is sigma by 2 epsilon 0 because of this. Because of this also it is sigma by 2 epsilon 0. So it will be 0. But outside here, that side and this side, sigma by 2 epsilon 0 because of 1. And in the same, this is a positive charge. Once again, I told you. Sigma by 2 epsilon 0 like this. So how much is it? Sigma by. So if I've got two positively charged sheets like this, infinite sheets, in between E is 0, but outside it is sigma by epsilon 0. But if I took one plus the other minus, what would happen? You tell me. In between here,
in between it will be there
sigma
outside.
by 2 epsilon 0 because of that one, and sigma by 2 epsilon 0 because of this in this direction, isn't it? For a minus towards it, for a plus away from it. Hello. So the field will be in the middle, sigma by epsilon 0, but outside 0. Hope you followed, everybody. Why? Plus charges will be like this, minus charges will be towards it. So they are opposite with the same magnitudes. So outside it will be 0. In the middle of them it is sigma by epsilon 0. Do you follow? Hello.
Yes.
Children, others, tell me.
Yes.
Sudhir, Sai Sudhir. If you really follow these things and if you can apply these things, you don't require anything more than my class work. Only you require to practice a little, Sudhir, if you're really understanding it.
Yes.
Not vaguely and broadly, but clearly, once for all. There should not be any gap in your understanding about it.
Yeah, yes.
If there's a gap, you'll get confused later. Not not broadly, not vaguely. You understand the meaning of it? Like some plus minus, so this one minus plus something, that won't work. You need to really know why it is this way, why it is that way, why is it becoming 0. All that if you follow, slight changes are always there in questions. Try to understand. Hello, any other doubts, children? And remember, you should need to understand that it's independent of the distance, whether you take here doesn't matter. And I explained it in for a disk thing, if you remember. Do you remember? I took a circular disk last time. Yes. and applied Coulomb's law and got that at a distance x from here. Can you tell me? I'm talking this again and again.
2k sigma pi.
2k sigma pi into
yes
1 by x by root of something. Am I correct?
X square plus r square.
But the same thing would become same formula here if x is tending to 0. I told x is tending to 0 is also equivalent saying r is tending to infinity. That means for an infinite disk of charge is nothing but a sheet of charge, basically. And you know that this becomes 0 and you get E equals only 2k sigma pi. How much is this? 2 into 1 by 4 pi epsilon 0 sigma pi. What do I get? Sigma by. So this and this are same, you see.
Yes, sir. That time also we did a sheet.
But you need to understand, I took for a finite disk and I extended it to an infinite disk. So you need to deliberate over it. You need to discuss it. Discussion, you will remember, not blindly you remember. You cannot. Physics is not like that. So we are almost in near completion of the discussion, but of course, more applications and more problems I'll be showing you tomorrow on Gauss law. I don't know whether people are writing only. The best way you learn and improve, I'm telling you, you cannot sit like this like fools. Of course, if you're understanding everything thoroughly, and I believe it, there's no requirement to talk, but I know very well that you're not understanding it, or you don't really know what is happening. So the best way to improve is to talk. And remember, you can decide whether you understood it or not if by putting that in words. If you're not able to put that in words, you're not understanding it. Finish. Very simple thing for me. Okay, Tejas Tamarana. Why are you not coming regularly? First, learn the subject, Tejas. Talk in the class. Hello, are you listening?
Yes.
Okay, I shall close right now. I hope people have written down this. I've given you in a clear way here as good as possible. So, hope that you're writing. So, can I close?
Yes.
Thank you.
Thank you, children.